All right, so let's get started. And I will start by answering some questions. I'm going to answer Saeed's question first live. All right, so Saeed has a question from the last lecture about which convolution filters we are using. And it is similar to a question somebody else had as well. So we're not using any specific convolution filter. So there are different kinds of predefined filters that people use for computer vision like applications. But the beauty of this machine learning approach is that the filters are themselves, they are learned as well. So when we are computing the loss, we don't define any filters. They are randomly initialized, and then as we go along, the filters are learned as well. So there's no specific filter that we have to choose. All right, and then there's another question about the order of things that I'm covering them in and the schedule of topics. So we were a little behind because I wanted to cover the basics in a way where things are progressing so that you understand, you have a good base and foundation. And I think after this lecture, we would have caught up. So maybe we're like a half a lecture behind, but the topics that we're covering, they may not align with the initial list that we had started out for the course, but it's okay. I think as long as you're learning and we are progressing, it's fine. So it's such a vast field that you can spend like a whole year just learning one of these things. So my idea was to give you a good enough introduction so you can go and explore after these classes. So it's okay if we don't fully match the order of the things we are doing them in. And as surveys come in, I try to gauge what people are trying to learn and understand. So I'll adjust the pace accordingly, but by the final class, we will have covered most of the topics that we started out with. All right, so let's see what we did last time. So this is class 6, and we have 3 more after that. And today we're going to do quick recap, and then we'll start with transfer learning. And this is going to be exciting because we're going to be building a useful system that we can actually use in practice, and hopefully for good, because it's going to be a facial recognition system. And as you know, it's been in the news, not just lately, but for a while, just for all the bad reasons. But there are good applications of it, and we'll see how to do exactly that kind of thing. So some of the questions that came in last time, is there a bug in line 7 of the code? So it is probably a typo, cut and paste. So this part is actually right. The patch width equals patch height. So I just wanted to emphasize that, and not just because somebody pointed my typo, but because of the way we do images in matrices. The 0, 0, or the origin is at the top left. It's not at the bottom left. So width becomes height, height becomes width. So rows and columns, they're kind of switched. So this part is okay, but I think I also had patch height as patch height as well. So you need to swap the height and the width. But in this particular case, it doesn't matter because they were square. So that's okay. Next question is about, like, are feature maps just multiple sets of patches? So you can think of that. You can think of feature maps as some condensed version of the image that they operated on. And instead of getting one patch, you get like multiple things out of operating a filter. So they become like multiple patches. And the patch sizes would be the same depending upon your filter size. Next question from Isan was about how do you make sure the temporal coherence is there? So when you are dealing with the sequence of images that are kind of part of a film or a movie, then you want to worry about like whether time-based data is captured as well. So in those cases, you may want to train with 3 images at a time or 7 images at a time. So you can stack the images. So we are currently training with 1 image at a time, and that itself is a stack of R, G, and B. So, but there is nothing preventing us from making a deeper stack. So you can have multiple frames stacked together. So if you have 7 frames, you essentially have 21 layers each of RGB for 7 frames, and you can train them simultaneously. So as you already probably learned that there is no image, it's all numbers. So the way we are abstracting it to be an image of R, G, and B, or if grayscale or anything else, is all up to us. So essentially, they are all large matrices or tensors that you can do pretty much anything you want there. Next question is about pooling. So pooling in convolutional networks is an intermediate step here that you see something called subsampling here, or so this is also called pooling. So pooling is another way to reduce the number of nodes. So as we do filtering with the convolution, you already are reducing number of nodes and the weights are shared because of the overlap of the filters. But then you can do another step where you take the maximum of those instead of using the filter size. You can use a smaller number and that you can just do a maximum. So subsampling or pooling is just taking the two kinds of pooling, max pooling and average pooling. Most people use max pooling and you just take the maximum out of that. So it helps you kind of reduce the number of nodes further. And if you have enough resources, you don't need to worry about pooling, but it's a good practice to have a pooling layer right after the convolutional layer. So again, when you remember that we started out with like a simple, fully connected network is capable of doing everything you want to do, except the number of nodes increases and it becomes resource intensive. So the CNN is one way of reducing the number of nodes by having a shared feature map, and then also by doing this extra pooling. There are other methods to reduce the number of nodes. There is something called dropping, where you can essentially just drop the number of nodes randomly from every step, and that also works because there's multiple nodes, so it's okay to drop a few of them. So there can be some different strategies for just reducing the number of nodes. And ultimately, it's all about creating efficiency so you can train your network in time. So that was pooling. Number of layers is 3, and why do I choose the values I choose? Again, these questions come up again and again. I think these are all some form of hyperparameters that you have to play with and adjust as you build your network, as you train your network. So all the items that I talked about, including the number of epochs to train, number of layers, number of filters, sizes of filters, all these become hyperparameters to tune and try different values out for. And this is more of an art form. And I think you'll be spending a lot of time when you actually solve a larger problem, adjusting these values and training your network for optimality. All right. Next, filter sizes. So that's a good question. So you always see filter sizes as 3 by 3 or some even number of squares, and never as a odd number of squares, or never something like 4 by 4. So the reason for that is when you have a 3 by 3 or a 5 by 5, it's odd. So there is an actual center. So that's the center part that you average everything to. So 3 by 3, 9 pixels become 1 pixel, and you can set the value of that pixel. When you have 4 by 4, so you don't know which one to choose. So you can choose one at randomly, but there is no real center. So it can cause some distortions. So most people stick with even or odd number of pixels for their filter size. And I think recent research shows that the smaller the number is, the better it is. So 1 by 1 doesn't make sense. So 3 by 3 is the next best thing. So most everybody now uses 3 by 3 filters. So this is a repeat of the question I answered earlier. Like there is no specific filter. You just learn the filter as well as you're learning. Denoised image is smaller than the original image. So that's not true because we are we have the same size, right? So you can input any size image and then denoise it, and it would be the same size as well. So there is some greenish cast compared to the ground truth. So you'll see that in CNN, a vanilla CNN like we did, it's not trained enough, it's not dense enough, there are not enough layers. So you'll get some averaging of colors. That's the nature of the CNN, because that's what it does. It's kind of doing a simple weighted averaging. So because these are satellite images, there is some kind of a green cast or some other artifact that you might sometimes see. And a UNet is a good good network to use to bring in some of the features from the earlier layers into the later layers. So again, it's just a matter of training more, and I think that should get fixed. Next question, if you have a noisy image, but you don't have a ground truth, how can you denoise it? So that's another good question. So it's a problem. So it's not, because you don't have anything to fix to, you don't have a goal, like what does denoising mean and what does noise mean? How can you learn it? There have been some advances in figuring out how to do that, and maybe I'll have some time to cover that via some adversarial networks, but you still need some example of what a clean image might look like. It may not be the same image that is a high res or a clean image, but you can have a clean image, like which may be different. So you can use that to train. So you just need an example of what a clean image looks like, not the clean version of the same noisy image. So that's one strategy to combat that. All right, so that's all the questions. So we are going to just do a quick recap. So you figured out what the CNN was. We understand convolution happening, and then some way we are reducing the number of nodes because of this convolution that happens, and you can do an optional subsampling or pooling as we talked about. So in the homework, I had asked if you can try to do other kinds of denoising. So this is not denoising, but we are calling them denoising. It's image degradation that you want to fix. And these are two functions that if you had time, you could have written. And I know some people did try, they sent me email, and the results look good to me. So here what I'm doing in this first function is saturating the image. So I'm using this TensorFlow method to basically just adjust saturation, and I'm using a default factor of 1.5. So the image becomes very colorful, the saturation value increases, and then we use that as an example of the noisy part, and then we send the original part. So that's straightforward, it works. You will notice that if you reduce the saturation, it still works as well. It will add back the color, but only to a certain degree. So when you have a totally a grayscale image, it is not able to recover color fully. And that's also one of the drawbacks of this plain CNN, is that recovering color is not as easy, because if you look at an average image, the average image is actually gray in color. So when you have this averaging effect in the CNN through the filters, the color recovery is not as bright. Individual objects don't really get their color back. So, that's something that is an ongoing research area. It's not fully solved, like how to color a black and white image exactly, because you want to color individual objects. You want to figure out what is grass, what is sky. So that sky remains kind of gray and blue, but the grass becomes bright and green. So this is something you can see and try to figure out. Second example is of down-resing an image. So an easy way to down-res something is to scale it down. And we are scaling it down here to 100 by 100 size, and then you scale it back up to original size. So just doing that with a filter that we're using for resizing called nearest neighbor, and that's like the worst filter you can use, and that causes the image to basically get pixelated. So if you decrease it a lot, then essentially you'll get like big blocky pixels. And this works pretty well. You can try that out. And the third example I had was you could try to punch holes in images and see if that works. And I can send the code out for that too. It's a little bit more complex, but not a whole lot. So in the example that I was trying in my notebook yesterday, is that I cut out these holes in the images, and I'll try to see if I could fix that. So looks like it did fix it. So that's pretty good. Something else is good. Okay, so try this out, and I'll send the code out after the class if you want. And that was the homework. So let's move on to building a facial recognition system. So like any other problem, you are going to first look at what needs to be done, right? So you want to build a facial recognition system. You think in your mind, like, forget about machine learning, neural networks. How would you build such a system? So there's the camera in front of you, and you go somewhere, and they take a picture of you and try to figure out who you are. So the only way they can figure it out is if they have some database of some version of your previous picture. And then they can compare the new picture that they just took with the stored image that you have. So let's try to design such a system first without thinking about machine learning. So you can, if you just think about it a little bit more, like what would such a system look like? So imagine you have a camera somewhere here in the image space, then you take the image of the person. So the image might be wide, there may be the person's face is in the corner, and maybe there are too many people in here. So you want to take the face part and extract it from this image, and that's the second box here. Are you guys able to see when I move my mouse or not? Hopefully you are. So, okay. So otherwise it wouldn't make sense what I'm saying. Excellent. So then you extract the face part, and then hopefully you have some database of known faces, and then you would compare this extracted face with the known faces, and if there is a match, and then you can say, yes, this is the person, and that's the basic facial recognition system. And we can explore each of these boxes, how to do those things, and then and only then we can say, okay, this part we can do with machine learning. The other part is this is the camera system we need to put up together. So let's go into more detail of the first part. So first part is we need to extract a face. So this is not identifying anybody. We're just extracting what a face looks like. So let's do that. So this is in a bullet form. This diagram kind of looks like that. Read the input stream, take the face part, and then compare it with the stored ground truth and identify the person. So for identifying the face part, again, not an exact like whose face it is, but just that something looks like a face. There's been filters like that for years in the computer vision community, because facial recognition is not new. I think people have been trying to do this for years in different ways. So there is something called a Haar cascade, and it's basically a set of convolutions. So those convolution filters, as you see in this image, they are moving around, and they try to find this pattern of two eyes, nose, and a face. So there are these 4 filters that kind of act on a box of image. And at the same time, this box, the red box that you see in the image, that is moving around throughout the image, trying to locate a face-like region. So, this is pretty common technique. It doesn't use any machine learning. It's basically just a filter, and it can help you extract the face or just the facial region for somebody's picture. So this filter kind of relies on just this empirical data about what the proportions of eyes and nose and faces are. And as you will see in all kinds of facial recognition system, it depends on the data that you give it. So it has all the biases of the data. It has all the problems and issues that you see in the news today of why these systems need to be more robust, need to be trained with better data outside of all the security issues and personal issues. So we're not going to get into the politics of it. We're just going to look at it as a mathematical and computer science problem. So let's keep moving. So how do we do this with machine learning? So the good thing is, so this lecture is about transfer learning. So where you're not going to write much code about neural networks, but you're just going to use other people's code. So that is called transfer learning. It's a nice way to say transfer learning because you're using somebody else's network. So there's a lot of research that is going on in this field. There's tons of models out there, tons of pre-trained network, and you can take those with permission and add in your own data. So the beauty of these things are that you can take the network, you can plug in at any layer. So you can remove a couple of layers and add in your own layers. You can, that's one way of connecting with somebody's network. Other may be that you don't change anything, just push in your data. So that's another level of integrating. And the last one, maybe you don't even do training. You just use their weights. So they have already pre-trained with a complex set of data, and you just use their weights. So for that to work, the output of their network has to be something meaningful that you can use. So there are multiple levels at which you can connect to other people's network, either just at a layer level or at the data level where you train it on your own data, or at the final level where you just use a pre-trained set of weights from other networks. So we're going to do exactly that for figuring out how to figure out the faces. So this particular network that we are going to use is called MTCNN, not MT, but MT. MT for multitasking. So this particular CNN is called multitasking because it does three neural networks in one. They're combined together. And what it actually does is very similar to the Haar cascade. Instead of moving things around in an image, it essentially makes a pyramid of images of multiple sizes. And then it has this predefined kind of filter that tries to find the features. It finds the same way it finds eyes, nose, and 2 points on the lips. So that's how it works, and you can read in more details. It's a published paper. It's one of the most used networks for doing any kind of facial recognition. It's pretty performant. So it solves multiple problems. So with the simple Haar cascade, the problem was that if the face is not fully straight and aligned, it may not work. And it doesn't work properly for faces in different lighting conditions. So in this particular example, you'll see that this head, make it bigger so you can see it. So this particular face is at an angle, and it's still working. So that's pretty good. So that's exactly what we want. So which means that they've trained this network with so many different faces in so many different lighting conditions and slight angles that it is still able to work. And it works on multiple people in the same image at the same time. So very performant, very nice network. It works in real time because it's very, very fast. So if you had instead, if we were doing this on our local machines, you could connect this up to your webcam and be doing this facial recognition in real time. So remember, we're not doing like facial recognition. We're extracting a region that looks like a face. So it's not a specific face, but just this box and these 5 dots. So the article of the paper, you can go through that. The PDF file should have a link to that as well. So again, it's called MTCNN. You just Google MTCNN and you should get that. It's a very popular paper, lots of implementations out there. So we are going to be using one of the implementations for this. There we go. Okay, so that's what our first task would be today. Let's go to this file. So for some reason or the other, this MTCNN, they haven't updated in a while, so it still only works with TensorFlow 1.x. So we're going to use that for this lab only. So let's load that. And we are going to be using another library called CV2. So it's a computer vision library, very popular, very nice and full featured. So we're going to use that to kind of display images as well. So MTCNN is available as a Python package, which is good for us. We're just going to install it using pip. And it looks like it's already been installed. So all you have to do to use it is instantiate it. So you're going to import it and then just create an instance of it. And another new concept I'm introducing is to be able to download different files from the web directly. We use this curl package. And anytime I use a bang here, which means I'm calling some Unix command. And this curl command, remember we have a full instance of some machine with RAM and disk here, and it's a Linux operating system underneath with a virtual Python environment. So calling this curl method, and it goes and downloads this file and names it as this. So I'm calling it Pixney Faces and getting this file. And now I'm going to use the computer vision library to read this particular file. So now I can treat this thing that I downloaded from the web as a file. So it's a JPEG file in particular. And I'm going to read that and use CV2 to show it. So let's see what this looks like. So this is basically a grade of many characters from Disney Pixar films. And we're going to use this as an example to identify faces. So again, not recognizing them, just identifying the region that makes up a face. So the way we use it is we just call this detect faces method and give it the image. And what this will do is it will return us a big structure called faces, and it will identify multiple faces in the same file. So that's good. And then for each face that it identified, it will give you some information. In particular, it gives you this information enumerated by this box. And it contains the X, Y starting position of the facial region and the width and the height of the facial region. So that's all we need. I think it gives you additional information that we won't be using, like where the eyes are, where the nose point is, and where, let's see, this faces thing. And then also where the 2 points on the face, mouth are. So we're not going to use all those 5 points. We're just using the box part. So then what we do is we use the CV2 library to just draw the box. So this means take this image and draw a rectangle starting from X, Y, and then that's the opposing diagonal in red color with line thickness of 1. So that's all this call does. So let's draw rectangles on the faces it identified. So this is just a function definition, and what we're going to do is call this function here on our image. So this quirk in the CV2 library, it internally it reads things in BGR format for some reason, and everything else uses RGB. So we convert it back before we give it to empty CNN. So again, don't worry about it. It's just a quirk. So we show the final image. So there you go. So it looks like it identified most of the faces, even though these are cartoon characters with disproportionate faces. The MTCNN is not trained on cartoon characters. It's trained on real live people. So it still did pretty good, so, which means we are making more and more characters that kind of have human proportions, except for the eyes here. So looks like it's doing a pretty good job of identifying a nice rectangular region where the face is. So we'll use this in our next step. Okay, so that's good so far. So it's a good place to stop and see if we have any questions here. Right, so not many questions. So somebody suggested noise to noise. Noise to noise is a good paper. So it allows you to denoise from essentially noise. So you take noise as a negative thing to avoid, and I think so. This paper is kind of complicated, but it's a good technique. I think that's something we were looking to implement as well in different ways, but it's pretty good. So end-to-end, what is end-to-end system mean? So end-to-end system means that you don't intervene in between. So you can set up. So if you are solving a larger problem, you may need to have multiple neural networks kind of chained together. When you do that, you are not only like just getting the output from one network and putting it into the input for other network, but you're also training them all simultaneously. So you can think of this long chain of networks, but it's not like a normal computer program where you have input from one function going to the output and so on, but it's training together as well. So you can think of it as this one giant system that is getting data from one end and giving you output from them. And so that's called an end-to-end system. And what we are doing here is not technically an end-to-end system, because we are basically taking MTCNN, getting the facial region from that, and then using another network for something else. So that's like there's a break in between. We are still using different networks, but it's not a fully end-to-end machine learning system. It's still an end-to-end system for facial recognition, but it still works. Okay, so that's the question. So let's go to the part 2 of it. So now we have some idea. So we did 1 and 2, which is we got the faces, or we did 1. We got faces from the ground truth images. So we're going to take and find out the facial region. So now we need to save save the ground truth images. So you're not going to compare pixel by pixel, because that's going to take too long. So what if we could take somebody's face and encode it in a simpler way? So it's easy to compare two faces without having to do pixel by pixel comparison. And pixel by pixel comparison may not be right anyway, because what if somebody is in shadow, or somebody has makeup on, or like people look different day to day. So if you do pixel by pixel comparison, you may not get the right answer. So you want some encoding that is invariant of a little bit of translation, that is invariant of a little bit of a change, but is focusing on these key markers of eyes and face and nose and mouth. So you want to still be able to recognize people, even though they may have changed slightly. So what you want to do is encode the images in some way. So once you do that, you can save that encoding, And now, say this person comes in front of the camera, and you are going to isolate their face, you are going to encode their face again, and then you will compare that to the stored encoding. And if there is a match, you are going to say, yes, I have recognized this person or not. So let's move to the second part, which is how do we encode these images? So we are going to use another network for that. And that particular network is called FaceNet. And there is also a paper about it, and it's a fairly recent paper kind of in this field. Nothing is recent because things are changing so fast. It's a 2015 paper. It essentially does the encoding or the embedding of a face. And the way it does it is by using this thing called a triplet loss. And intuitively, you can think of that as if two faces are similar, then you want them to be as close as possible. And if two faces are different, you want them to be as far as possible. So the more different they are, you want them to be farther apart in the encoding, right? Because we're going to be comparing encoding. So you want the encoding in such a way that if two things are similar, they are close to each other. And if two things are different, then they should be far apart from each other. So these two equations here, and that basically are if you have the input as face A, and then you have another face which is close to it, you want to minimize this loss. And if you have a face that is farther from you, which is a negative face, then you want to maximize that number. So that's why the minus is here. So by doing this joint loss, you can create an embedding or an encoding that places similar faces closer to each other and dissimilar faces farther from each other. And the result of this particular network is a 128-dimensional vector. So it's just a vector with 128 numbers. So it's 128-dimensional vector, which gives you essentially some kind of a number that encodes a face. So now if you have to compare two faces, you will encode them using this network. And for both of them, you will get this vector, right? So 128-dimensional vector. And to find if they are close to each other, all you have to do is find the distance between the vector. So you already know how to find distance between two vectors if they are in 2 dimensions. And in 128 dimensions, the formula is exactly the same. So all you have to do is find the distance between the vectors pretty fast. It can be done at an interactive rate. So it's very easy to compare two faces using this particular encoding. So let's use this network now. Let's go to this file, facial recognition 2. So things are going to get a little bit complicated because we are not only going to use 2 of these networks, we're also going to use some images. So I had asked you to send me a couple of images of yourself in different lighting conditions, different times, and some of you did. So I uploaded them. If you go to if you go to the drive, you will see a new directory there called Faces, and it should have all the faces that I uploaded there. And if you don't see it, just refresh it, and you should be able to see. So you're going to use some packages, install MTCNN. Make an instance of it. So right here, what I'm doing is I am mounting the drive. So because I don't want to upload each file one by one, I'm just going to use my drive to get access to the folders. So if you look at the folder part, it's all like this. So I'm going to mount my drive using this particular function. And it is asking me to go to that. And I'm going to use one of my accounts and allow it permission. Hopefully it's not, then it gives me a code. Now where were we? And then put in my code here, and it allows me to mount my drive. There you go. So refresh it. So my drive is now mounted here. So this is my Google Drive. So in my Google Drive, I have created an alias to the course folder that has been shared with us. So that is the course folder. So these are all the things that are already there. You have access to. Then I added this directory called Faces. And easy way to do it, like these 3 dots that you see, if you click on them, you can get the path for this folder. So that's what I did, and I put this path here. So it's nothing special. You can get a similar path, and this is my alias for this folder. So in addition to the faces themselves, so if you look at this folder, I have all these faces of people who sent me their pictures. Thank you for doing that, by the way. It's, I know people are wary about sending their pictures, but we're going to delete everything. In addition to the face images, I have also uploaded this particular file. It's a FaceNet keras. So it's a set of weights and the model for the FaceNet network. And we're going to be using that as I just described earlier. So another good thing about the FaceNet is that we don't have to train anything. And the reason we don't have to is because it's just giving us a number, and we can give it any face, and it will give us a 128 dimensional vector, and it doesn't matter what the face is. Because it's automatically going to put it closer to the face that are similar and then farther away from the faces that are dissimilar. So it's kind of a nice way to get this independent encoding that doesn't rely on training. Otherwise, we would have to train with all these people. We need to get like 10 or 15 variations of these people's images and train them. So FaceNet kind of has this nice property because the embedding is just a 128 dimensional vector. We don't have to do any training at all. So that's it. So we are going to load that FaceNet model from the drive. And let me just close this so we have more space to see. Okay, so this it's going to load it up from the drive. It takes some time sometimes. Okay, so it's done. And this is just the code we had last time. We don't need this. So I'm going to just basically have these names and faces. I think I added one more face that came in at the last minute. Let me see. Andrew, Martin. So this is Sabrina. I'm going to add her name as well. Okay, so I think I got everybody now. So all this is doing is creating a small dictionary with names and files. So because we want to have the names kind of nice and clean here without the file name part. So that's all it is doing, is creating a small dictionary. So let's take a look at these faces. the files are of different sizes. It would have been nice if they were all the same size, but that's okay. We'll see what happens. The whole thing is about learning. So that's me, Alberto. I got the double scrolling thing again going on. So I've labeled everything as the name from the image, and so it looks like it's working. We got the images, reading and writing is working. So that's like a lot of times you want to do that. You want to be able to debug as you go. So make sure one part is working before you kind of jump into the next part. So essentially reading images and displaying them is working just fine. Okay, so that's all good. So now I have a bunch of functions here, and I'm not going to go over each of them line by line, but I want to cover essentially all the way from the bottom, some of the things. So essentially, we are now going to be given all these faces that I had just listed above. So we are going to encode them. So encoding is done using this particular function. The first thing we do is we get all the names from this dictionary that we have and the images. And using the empty CNN model, we get the face part out. It's a rectangle. And for each of those rectangles, so this is the rectangle, we encode that. So basically we don't need to encode the entire image. So we just first need to find out just the face part, so which we do using empty CNN like we did before. And then we encode it. So encoding involves, again, we extract this part from the image, the face only part, and then because the FaceNet model expects the image to be of this size, we're going to resize it, and it also expects values to be in a certain range. A process called whitening, which is some kind of a mixture of standardization and normalization. So we are going to whiten that. It's essentially a form of normalization. Once we do that, then it's ready to be predicted by the FaceNet model. So that's one thing you have to worry about when you use other people's network, is to find out what kind of input they expect, because slight variations in the input make a big difference. So if we did not resize it to 160, or if we didn't normalize it, the results wouldn't be as good as it would be. So you want to know what are they expecting, what is the expected input, the sizes, and what else do you need to do to the data. So we're going to predict that. So prediction will give us an encoding, which is going to be the 128-dimensional vector, and we're going to return that. So for all the known faces, we are going to save the encoding out. So that's all we need to do. And for the known faces, we are going to expect that there is only one face in that image, and we're going to break it out so we don't have to go through all the boxes. So that's how you encode it. And this encoding, say if you're installing it at your workplace, you may do it during the time when people first day of work, when you take their picture, or in some way where you have a clean, nice encoding of their image that is kind of free of all kinds of different trees or vegetation or lighting conditions. So it's an ideal picture that you use the encoding for. So that's your database now. So we save away the database. And the next part is now given a different image. So say now I'm going to be given a different image. So I have this image that I made by composing everybody's face. So this is actually a single image. that I'd made with everybody else together. And this is a different set of images than we did the encoding with. And that's the whole point, right? So these are in different lighting conditions, different posture. So our challenge is to kind of, can we match the one we encoded with this particular one? So given a new image, what are you going to do? So given a new image, we are going to identify faces. So to identify faces, we are going to follow a similar process. First, we are going to find the facial region. And there may be multiple faces in this image, so that's okay. So we're going to go over them one by one. We're going to find the box of the facial region. We're going to encode the facial region. And then we will find the encoding that is closest to this encoding from our database. So that will give us the distance from this particular encoding, and we'll get the name for that. So this is essentially just doing a difference between the two 128-dimensional vectors, and we use something called norm from the linear algebra package, and it basically gives you distances. And we'll find the minimum of that distances from the saved encodings and find out the name from the list, and that gives us the face that has the minimum distance and the name of the person that has the minimum distance. So once you get that, so now this distance is just a number. It's a single number. It can have different meanings depending on context. So we'll have to play with this to what is the threshold that we should use. So we can do this by experimentation, because if you install this system in a place where everybody looks a little bit similar, then the threshold may be lower, because you want the faces to be very closely matching to make a differentiation. If you have a wide diverse array of people, then you can have a larger distance, and so that should be okay. So that's a trial and error. You try it out, what threshold works for you, and then we'll just to make sure it's working, we're going to print that distance and the name. And to visually show this, because you're not going to be looking at distances, to visually show this, we're going to draw a rectangle. Again, a red color rectangle with 2-inch wide pixels, and we're going to put their name on that. So this will basically, on top of the image, we're going to put the name. So that is just on the rectangular part. So hopefully that's all clear to you. And let's run this on this particular image and see what happens. So what we'll have to do is start from the beginning and execute all of these functions. So we did this already. Let's do this. Running. Okay, so now it's doing that, encoding the known faces, done. And we did this already, so this is showing you the input image from which we wish to find out the faces. So let's do that. So it looks like these are the numbers it got, these are the minimum numbers, and these are the names. So next thing we're going to do is display these and write the names on each of the images to see if it worked. So there it is, and looks like it's worked. Anybody in the class whose image is up here? Does it look right to you, your name? I don't know anybody. Just reply in the chat if it is correct. Okay. So I think we've done something where like the image that, say for example, Lou's face was encoded on was totally different, not totally different, but like he had, let's see what it looked like. Oh man, scrolling for multiple scroll bars is a pain. So I'm going to show you the original images that we encoded with. Sorry about the scrolling. So let's take a look at, take a look at Sabrina's image. So this is the last image we had. So this is what we used for encoding, and the image that we recognized as. So it's pretty like different lighting condition, the angle is different, and it's still able to find it, and that's pretty good. So where it failed was this image, right? So it's a very drastic 90-degree turn. I'm pretty sure if we turned it around, it would fix it. And this particular one, it also failed. So you can see, because this person now totally looks different, and this kid's picture was not part of a database, so that's fine. So this was not recognized, and this particular image was not recognized as well. So now you can see when you go to the airport, why they ask you to remove your hat and glasses is because these systems get confused if you have some drastic change in your appearance. So remember that if you are in a public space and you want to fool these systems, all you have to do is put on a hat and put on some sunglasses and you'll be fine. So that's the lesson to learn here, that these systems are pretty powerful, and I think we have used a couple of publicly available systems to do this, but still able to get, without any training at all, get very good results. I'm always surprised how well this works. So we are using this on a cloud environment, so we can't hook up our webcams, but if you're interested, maybe next time I can send you some code that you can do this on your webcam in real time. And it works. It's pretty fast, this code. And you can detect in real time as you move your head around. And that way, I think you can test the limits of the system. You can stare at the camera, it will identify you. And as you start to turn your head, you'll see the percentage of identification decreases until it kind of starts failing. Or if you have a bright light shine on your head, if you wear glasses or hat. So it's going to be pretty cool. So we are out of time. So let me give you some homework that hopefully is interesting and you will try it. So we will cover variational autoencoders next time, and generative adversarial networks. So those two kind of go together, and it's a nice thing that kind of landing up on the same class. So for the homework, go ahead and download, like say 100 celebrity images of different people, and find their encodings, and then find out, comparing to your encoding, what distance is the minimal. So you can that way find out which celebrity looks like you, or vice versa. So try that and see what happens. Hopefully this was fun, and I think I like doing practical applications so that you can do easily in a class setting, because otherwise it's hard. We don't want to just play around with the toy data. So this is fun. Hopefully you learned a lot, and see you next time. Thank you.